Yanagi told us to do is, well, let's change the color of this picture. Let's actually recolor it like that. Let's color this in red. Let's color this in green. And now you see that this red curve is some curve that bounds the subsystem B. Right? It's not a minimal curve, but it's some curve. Whereas this green, like, sort of piecewise continuous arc, bounds this joint system ABC. Again, it's not a minimal curve. So in general, what we will get now is a lower bound, right? So what we now just proved is the strong subjectivity entropy inequality. Because, like the minimal curve will be something like that. The minimal curve there will be something like that. Now, I mean, this is very pretty, right? It's sort of, especially when you compare it with like proofs, strong subjectivity for the von Neumann entropy, which is quite a bit more involved. Of course, making this precise actually required, right? I mean, this was more of a cartoon, right? To make this precise, I should look at arbitrary geometries, arbitrary boundary regions, and then maybe it's a bit more tricky to write down these things. But it still has a very combinatorial flavor. And so the method that we propose is basically to take this, to take this idea of doing basically, it's kind of like an inclusion-exclusion-esque principle that we use here. And it's actually to write down a combinatorial version of this which works in general. And basically, let me illustrate how this goes with a concrete example. Let's suppose we want to prove this entropy inequality. So this is like an entropy inequality for 3 systems. That's the entropy of any, the sum of the 2-body entropies is largely equal to the sum of the 1-body entropies plus the overall entropy S of ABC. So I will not go into the proof. So I just want to sketch you like how completely mechanically you might be able to prove this entropy inequality using our method. And so what we do is the following. So we take all these subsystems A, B, and C that appear. We also add a reference system, which we call O. It's like, like a purifying system, if you like. Then in each row of this table, we write down what we call occurrence vectors. So an occurrence vector is a bit string, which is 1 if the region appears in the corresponding term of the inequality and 0 otherwise. So say A appears here, it doesn't appear there, it appears there, A appears again here, and it also appears here. So we get this bit string 101 on the left and 10001 on the right. Like this, you can do this for B and C. And of course, this purifying system, by definition, doesn't appear anywhere, so it corresponds to the 0-bit string on that side as well as on that side. And now the theorem, or the method that we sort of call proof by contraction, goes as follows. It says that if this table, where there's bit strings of length 3 on the left and bits, so I can interpret this table as a partially defined function. It's a function from bit strings of length 3 to bit strings of length 4. If it is possible to extend this to all bit strings of length 3 in such a way that the one norm only never increases as I go from the left to the right. So that is a contraction with respect to the Hamming weight, the one norm distance between bit strings. Then the corresponding entropy inequality is valid. So this is what we show. And so just to reiterate, so what this says is like extend this table in some way to a total function. Take any two x values on the left, compute the Hamming distance, compute the Hamming distance of the corresponding bit strings on the right. The distance on the left has to be at least as large as the one on the right. And it turns out that this is a very combinatorial way of modeling precisely this inclusion-exclusion game that we sort of did by hand over there. So from such an extension of this function table, you can actually extract the precise construction. Like it's basically a witness for the proof in a very constructive way. And it gives rise to sort of a greedy algorithm where we can try to, you give me an entropy inequality, I write down this partial function, I try to extend it to a global function. And so we have sort of a greedy, say, strategy or algorithm. There's no guarantees that it will converge. If it does converge, we get a proof of the entropy inequality. It seems to work pretty well in practice. Good. So it turns out that the entropy inequality that we just proved is an entropy inequality that is not true for the von Neumann entropy. Let me just maybe check the time. This entropy inequality that we just proved is valid for holographic entropies, but not for the von Neumann entropy. And this has been actually observed in by a more sort of concrete and hands-on geometric proof by Hayden, Hedrick, and Maloney. It can be equivalently written the following way. It can be written as the mutual information between A and B plus the mutual information between A and C is less or equal to the mutual information between A and BC. So it's a monogamy-like property of the mutual information. And it is something that is just not correct even for the Shannon entropy. You could also rewrite it as follows. You could say the entropy of AB is less or equal to the conditional entropy between A and B conditioned on C. Whereas we have learned, I guess, well, we knew and we have learned again on Wednesday that the conditional mutual information being 0 has something to do with quantum Markov, with the quantum Markov property, whereas the mutual information being 0 has something to do with being a product, an independent states or random variables. So in general, there's no relation between Markov and being, the two endpoints being independent. Something that is some explicit state, for example, or some explicit correlations excluded by this inequality are GHZ states, say, four-party GHZ states. So this is kind of, I guess, this is kind of an interesting inequality, and I think we still haven't fully explored the consequence, like the sort of the information theoretic content of this inequality, which would be very interesting to do. Using our sort of proof by contraction method, we could prove sort of an infinite new family of such entropy inequalities. It looks a bit complicated, so it's an entropy inequality on an odd number systems, 2k plus 1. And on the left-hand side, you have a conditional entropy where you take one subsystem and you condition on the subsequent k subsystems. And you do this in a cyclic fashion. So this addition is modulo 2k plus 1 in that case. So for example, this inequality, if you subtracted the one-body terms, you move them to the right, then this would be the conditional entropy of A conditional B conditional C, and C conditional A. So this is a generalization, sort of an infinite generalization. And indeed, like it captures all the ones that people had established previously. We have also verified some entropy inequalities that are still currently conjectured for the von Neumann entropy. So unfortunately, there's no contradiction there. And the way by which we prove this is really we construct explicitly such a contraction. So we build this big function from bit strings to bit strings, thank you. And we show it's a contraction. So it gives like a rigorous proof of these, a rigorous combinatorial proof of these entropy inequalities. I guess, yeah, this was our first non-trivial example. So I guess this is some like 5-bit hypercube, and then we were happy and we asked some. Good. So maybe I should say a couple of words more generally on what we found for these holographic entropy counts. We find that for at most 4 subsystems, subadditivity and monogamy are actually the only constraints. So they fully characterize this cone, and we can identify geometries / graphs that correspond to the extreme rays of that cone. So maybe I shouldn't go into detail, and maybe I shouldn't explain these geometries in much detail. The upshot is kind of that these geometries have a sort of a nice interpretation to high energy physicists. So they can be seen as time slices of space-times that correspond to space-times that have several black holes in them, and behind the black hole there's like a multi-boundary wormhole configuration. So it's all so basically, this multi-party entanglement in the states, people try to relate to this geometry. So it's kind of nice that we found that we could always basically relate Poisson's entropy cone to this class of geometries. For more than 5 subsystems, we found several new inequalities. In general, we don't know the story. We found several interesting features, like, for example, we need geometries that have some higher genus. So, these kind of star-like, or, these kind of things that have like an empty bulk. And I guess those would correspond to graphs that are just like stars. So this would be a star with 2 legs, a star with 4 legs, a star with 5 legs. These guys, they have like, they have little holes. They have like higher genus. So this, I guess, is maybe interesting. Maybe the last, not really application, but something that was very much motivated by this work that I wanted to mention is this issue of random tensor networks that Patrick briefly discussed on Tuesday. So what Patrick told you about is basically, take an arbitrary graph, put random tensors wherever the vertices are, and take a high dimensional, take random tensors of high bond dimension, and so these are like maximum entangled states. These are the random tensors. If you do this, then this Ryu-Takanagi formula is actually satisfied with high probability. And we can make this pretty precise by using stabilizer states, where everything is quantized. And so what this shows, so this entire story about random tensor networks that Patrick talked about has this particular implication that actually all these Ryu-Takanagi entropies are indeed quantum mechanical, right? So it is indeed true that when you start with a geometry and a couple of subsystems, or say a graph and a couple of subsystems, and you define entropies in this geometric way, then I can construct for you a quantum state, and the entropies of that quantum state agree precisely with the entropy, this geometric entropies that you started with. And so this seems maybe funny because, after all, the Ryu-Takanagi proposal is a proposal for the von Neumann entropy. But what it means is it's actually a very strong consistency check. It basically means that, we can stop verifying strong subadditivity, etc. All these inequalities that are true for quantum states are now obviously true for this Ryu-Takanagi formula, because we can realize all these Ryu-Takanagi entropies as von Neumann entropies, as literal von Neumann entropies. And we can do so via stabilizer states, if you like, and you might like this. So maybe here is sort of a last sort of high-level point of view of this entropy cone business. So this gray cone outside is sort of the elusive quantum entropy cone, of which we know a couple of phases. We have strong subadditivity and its variance. Essentially, that's all we know. There's a couple of conjectured entropy inequalities. And some of us believe it has round features. Some of us don't. Inside this quantum entropy cone, there's the subcone spanned by the entropies of stabilizer states. Now, from what I just told you, inside there is now this holographic entropy cone. And so, this result makes sure that this inclusion is true. And again, just sort of to point out that, again, the phases of all of these cones, they correspond to the universal entropy inequalities that we care about. All right, so let me wrap up. So, sort of the main message, I guess, of this talk is that this idea of an entropy cone from quantum information theory is sort of a nice organizing principle, I think, to study entropies, to study holographic entropies, in particular if you care about these inequalities and sort of universal constraints. There's this equivalent combinatorial model provided by min cuts in graphs, which has a very computer sciencey flavor, so we can use ideas from linear programming, etc. And so this gave rise to this idea of proofs by contraction of new entropy inequalities. We could go back to geometries. We could also go back to quantum states, and so sort of up bounds and lower bounds in that way. Great. So thanks for your attention. So co-authors are not allowed to ask questions. It's a karma.
I just wanted to make one additional point that's relevant from a strings perspective. So in general, it's not known which CFTs are known to have well-behaved holographic rules. And so another way of thinking about looking for these entanglement entropy inequalities is it's possible that if you can show that all of the entanglement entropy inequalities are true, this provides a necessary and sufficient condition for the CFTs in question to be checked to see whether or not they have well-behaved holographic.
So I guess sort of the motivation from a high-energy physics point of view to care about these entropy inequalities is really you have a state and you can actually check if holography has the chance of being satisfied, right? If there is a sort of a semi-classical dual description. Yes.
So I have two questions. The first one is, how robust is this inequality construction to when the, say, Ryuta-Kanagi segment does not hold? Because this is like an area law, and we know in, say, condensed matter systems that satisfy the area law approximately, or there's a constant correction like topological entanglement entropy.
Right.
And the second question is, can one see this proof by contraction idea as a linear program?
So what was the first question? So the first question was like, what if the Ryuta-Kanagi formula is not true precisely? So all these inequalities that I wrote down, so people would say this is true in leading order, but indeed we know cases where this Ryuta-Kanagi contribution, say, vanishes in certain geometric configurations, and so sort of the sub-leading terms take over. So I think that's a very good question. So basically, when these entropies are all large, I think this is all these inequalities hold up to order 1, say. So if the sort of the geometric contribution is very large, then we are happy. But if they are small, then we are unhappy. So for example, maybe this is a good point actually. So I told you the story about how this is the mutual information, and that minus that is the condition mutual information. And so I put in quotes, this basically excludes non-trivial quantum Markov states. And the reason why I would say this is that, well, a quantum Markov state is one where this condition mutual information is 0, but now this inequality tells us that actually the mutual information is 0, so it should be a product state. But of course, such a statement is only true if you can really take care of the order 1 contribution. So this is precisely down the alley. It's precisely along the lines that you mentioned. And the second answer is that yes, you can think about this as a linear program, but it's sort of, if you write it down naively, it's a very big linear program. And like this, because somehow you want to encode this function. So it's like a function from like so and so many bit strings of length, say L to the bit string of length R. So you need many variables if you do in a sort of naive way, and we haven't been able to figure out like an efficient way. I think that's a very relevant, an interesting computer sciencey question, like, can you decide if there exists such an extension, say in polynomial time? I think it's a very concrete and interesting question.
Are you saying linear program or integer program?
Okay.
They're big difference. Is it a linear program or an integer program? It's 0, 1 for...
Well, so this seems like an integer program, right? Because there's zeros and ones in there. But there's certain ways of relaxing this. So I can relax the range of this function to be mapped into the interval 0 to 1 by modification of our method. And then indeed it becomes a linear program. Whereas because I mean, these are just like variables, so they're like fixed, like indices, and the right-hand side then would attain real numbers. Thanks, that's a good point.
So you argued that you could reduce wormhole geometries to graphs, but what about other geometries, and what about how do you obtain the continuum limit? Is it like an infinite boundary wormhole? Is that what you're saying? Maybe a CFT is, or like
so,
how
Right.
What's the continuum limit?
Right. So somehow, so the beauty of this method in a way is that we coarse grain. And so sort of we change the perspective, right? I mean, it's a very fair point, right? Because some of the perspective of this entropy cone, but indeed also of entropy inequalities, is that you look at finitely many pieces. And so from the perspective of these finitely many pieces, right, everything looks discrete. And this is basically what we formalize. For example, here, if I only ever ask questions that involve, A, B, C, and their composites, and actually I only ask entropy questions, then this is a very finitary problem. So this is sort of the vice and virtue, like so we can study things like entropy inequalities, but we cannot zoom in afterwards. Say, what we can do, for example, is like we could refine things, and then we get maybe an inclusion of these cones. We haven't explored that route much, I would say, but I think sort of by ignoring sort of like detail, I think we could sort of zoom into the question that we wanted to answer, like to study these entropy inequalities. It is certainly true that you lose a lot of physics by doing so, but you capture the entropies.
Let's thank the speaker again. So, because we have the two sessions, there's a 5-minute break for the next talk, which starts at 4:15.